The main idea of this presentation is you did first in high school. What now? Because when I was in that area, I got some interesting advice, and I kind of wanted to give my own take on it. Hopefully, you find it interesting. We'll see how it goes from there. There you go. So, I guess a little bit of history about me. So, I've been around tech for a while, and we'll get to exactly when I graduated and whatnot. But I started kind of my robotics journey in high school doing FTC, as you can see on the left. Um, I was around, this was 2013. I've been around for a while. Um, that's kind of where I got my start. I had a good mentor. I worked from there. I was like, I wanted to do robotics in college, applied to a bunch of different colleges for robotics. Then I got into Georgia Tech, decided to come here, which is where I currently am still. And I joined this thing called Robojackets. And Robojackets is kind of the student home of robotics, competitive robotics at Georgia Tech. And here's a picture of us from 2 years ago because of COVID. There's no picture from this year of the robot we had and the team that was there. Now that I've gotten pretty old with respect to Robojackets, I'm more there as a mentor than an actual participant, but I really enjoy that, and that's kind of where I got involved in that. Meeting some of the other guys I knew in Robojackets is how I got involved in my current robotics research, which is pictured essentially on the right. So those three PhDs on the right, Paul, Brian, and Grady, were kind of my mentors about getting into robotics research and continuing a lot of essentially right off of where Grady left his thesis off. And we could do some really cool stuff with that, and I'll show you guys a couple demos about that. And I'm always happy to talk about my research. So that's kind of my path through. Started in first, joined Robojackets, got more involved, and now I am. So I did my undergrad in computer science. I graduated in 2019. Then I started a master's in robotics effectively. But then I was like, oh, we'll just stick around forever. So now I'm doing a PhD in robotics. PhDs are a lot of fun. So my lab is the ACDS lab, which stands for Autonomous Control Decision Systems. So we do a lot of real-time controls. Like for me specifically, it's what's pictured down at the bottom. It's aggressive driving. So we have this Fitzco car, and it just goes all out, all over the place, and it's a lot of fun for research. So I also run a bunch of undergrads doing some autonomous research on that platform. I was also the Robojackets president for a year, been involved with them for 6 years. So I think I've kind of got the full, to somewhat degree, the full picture of what you can do with respect to robotics in college. I did the undergraduate research. I've run the student organizations. I do my own research now as a PhD student. I did computer science, which we'll get into a little bit later. That's me. So robotics presentation, we got to do a robotics demo. So this is some from our recent work, which we submitted to a conference about a month ago. So this car is fully autonomous. Fifth scale, the top speed we're getting here is about 9 meters per second, which is like 20 miles per hour. The top speed we ever get on this car is closer to 30 miles per hour. Here's some really nice slow-mo of what it looks like when it's actually going around. And the really interesting part of this research is how do you control that platform as it goes that fast with all of those disturbances? You could see the car, it was bumping all over the place, you were losing traction. Like all of these things just make it more and more complicated to do control. And how do you do that in real time? So kind of my approach for this presentation is I'm going to kind of cover some core topic areas of robotics, kind of break down some terms that you're going to hear a lot. As soon as you get to undergraduate, you might have already started hearing them in first, depending on where you are. I want to take those terms and be like, this is exactly what it means, and kind of show you the different flavors of robotics. Because a lot of times people come in, I work with a lot of undergrads, and they're like, I want to do robotics research. My next question is, what type? And then they kind of give me a look. So here's some of the types. I'm going to kind of butcher some, and I'm going to group things together that I probably shouldn't, and I'll probably leave some things out because I only have my own experiences to talk from. But we'll see how that goes. We'll talk about majors in college. I have a lot to say on majors. You'll hopefully be useful information there. We'll talk about what you can do in college. We'll talk about what it's like after you get out of college or you get into grad school. I'll give you guys some general advice, and then hopefully we have about 20 minutes or so for questions. I really like the questions. A lot of this is a really personal question answer kind of style. So feel free to ask those questions. So starting off, we'll do some core areas. So first, let's talk about robotics. So I've been doing it for nigh on a decade at this point, and I think the way my lab approaches robotics is very different than most labs. We kind of see robotics not as the necessary like the car driving around, although we do that, or the drone flying around, which we also do, but kind of this really general concept of there's a thing called a robot. It makes decisions and it can affect the environment through things called actuators. So for like first, this would be your motors, your servos, what have you, your grippers. That's what you can do, and you get some sort of feedback back, like your wheel encoders, your IMU, or camera. Then you use that to make more decisions. So this is a little bit more general than most people tend to think about robotics. And what that allows you to do is to kind of classify things that would not necessarily be robotics with the same algorithms that we use in robotics. So a really good example we'll talk about more later is there's guys in my lab. The guy to my right is doing vision-based navigation, so taking a camera and figuring out where to drive. The guy to my left is doing control of quantum systems. The guy down across from me is working on how do we do CPR. We're all using the same algorithms. We're all doing very similar things, but the applications is widely different. So first, let's talk about control. So this is kind of where I would say most of my research is in currently. So the basic idea of what control is we have some sort of trajectory or we have some sort of things we want to track. What this means is I know where I want to be for the next 10 seconds or however long that time period is. So then you're going to use this thing called a controller, and it's going to output a command, which is then going to go to your actuators. So then go to your robot. And essentially all you're trying to do is I want to be at these states. What do my motors need to do so that I reach those states? And then you get some sort of feedback, which is what through your sensors. So you have some sort of system state, which could be X, Y, yaw, so like your orientation of your robot, whatever it might be. And then you get some sort of measurement. Like often you guys will have IMUs, so you'll get an acceleration in the X, Y, Z, and you'll have some rotation rates. So combining all that together, we can get some sort of feedback to where we are, and we can change our controller on the fly as we go. Feedback is very important. So to show you kind of what I was showing, so what I was showing earlier is the same algorithm I'm about to show you a video of. So this is work from closer to 2015. And essentially what we're doing in this is, remember I talked about our trajectory? So our robot starts in a state. We have some sort of concept of what happens when we apply certain commands and where that will end up in the real world. So if I'm sitting here for auto rally, it's steering and throttle. I apply a certain throttle, I apply a certain steering, give me a second and I will be in this spot. So for this algorithm we're looking at here, it's called model predictive path integral. There's a bunch of fancy math terms to essentially say we do a bunch of rollouts. So we're like, what if I sampled a bunch of controls and just laid them out and see where they end up? And then I give them some sort of weight, and then I combine them together to make a better solution. And that's all you're seeing here. I really like this robot. It's just a lot of fun. I just get to race RC cars for my research. That's control. The next one a lot of people will talk about is this thing called computer vision. So humans are really good at context specifically. So when you and I look at something, I can give you like very limited pixels or like half an image, or something can be very occluded, and you are totally fine just inferring what's there without having to think about it. And that's really amazing. Computers are not good at that. They're really bad at that. And trying to figure out the differences of what I'm looking at and why is it important, or even just what is important in this image at all, is a really hard task. So what you're seeing here on the screen is we use these things called filters, and these are the really common ones that you start to use when you start to break down the images. And so you have Laplacian, Sobel, X and Y. So essentially all we're doing is applying this filter across the image, and then we're getting out some things. So these filters are all around detecting edges. You can see in that image, we're looking for edges, which for us is essentially a change in color. You go from black to white. Whenever there's a giant change from black to white, I want to know what it is. I want to figure out where it is. And you can get some pretty interesting results just doing that. The other thing I'll mention is all the research I'm showing is currently happening at Georgia Tech. So that's a fun school. This is a professor that I work with on and off. He also works on the autonomous race car, but this is more of his other research. He's doing a lot of machine learning. And essentially what he's trying to do is look at videos of people and figure out where they're looking. So this, he does a lot of healthcare related robotics, and this is really important in the healthcare field of, I don't always know if you're paying attention to me because I don't really know what you're looking at. And that's really important when we're trying to do an important procedure or whatever it is, or figure out where your attention's focused to see if you actually are understanding what the robot is telling you. So this is what that research is kind of centered around. So they'll actually generate a thing called a heat map, which you'll see in a second. This. You can see that, hopefully you guys can see my cursor. You can see this kind of red blob, and that is exactly where they're supposed to be looking. And there's this giant neural network we'll talk about in a second, which is predicting where that image is just based, where the person is looking just based on a bunch of images. So next, we have state estimation. So robots are not good at a lot of things. One of them is knowing where they're at. So very frequently in robotics, you're asking yourself, where am I? And that's just kind of a important question that we often don't have an answer to. So what you're kind of seeing here is a block diagram. So we have some sort of robot, he's in the world, they have some sort of readings, which are these sensors. You get some sort of sensor reading like you do with your IMU, you get some sort of noise. It's not perfect. You don't know exactly what your acceleration is, so you get this measurement Y, but you don't know what your noise V is. So then what you have is this thing called a sensor model, which is down here. So what the sensor model is I take my current state and I pass it through it, and it'll give me what my measurement should look like. And then I compare that to the measurement I got, and then I get some sort of error. And that's what's being used inside my state estimator to figure out a better estimate of where I currently am in the world. And pretty much a lot of the hard robotics kind of comes down to these like really basic ideas and concepts of what you're supposed to be doing in the world, which when you start to represent them become rather complicated rather quickly. So this is more work. This is a collaboration with people at University of Zurich. Yes, University of Zurich. This is with a guy named Frank Dellert, and he does some really cool things. So what we're actually looking at right now is a concept of SLAM. So we talked about localization, which is figuring out where I am. We haven't talked about mapping, but essentially mapping is what is around me and where is that. SLAM stands for simultaneous localization and mapping. Where am I and where is everything else all at the same time? So what you're seeing here is they're taking this image, they're generating all these points. These are important points from them. They're trying to figure out where they are in the world and where everything else is and map out the ground and the walls. And then they're generating this point cloud over here. This is kind of showing the robot, but the resolution is probably not good enough for you guys to see that. So what they're going to do is they're just going to track these points frame to frame. So we're applying the exact same kind of filters we were talking about earlier with computer vision. We're just looking for high changes in color, contrast, or whatever you want to call it. You get these points, you start collecting these points together, and you figure out where your robot has been over time. You can see they grab the person, which is obviously not a great landmark because people tend to move. But you hope that with enough landmarks, most of them are stationary and it's not a problem. So at the end of this video, they'll construct this whole map. So you can kind of see that they started here. They walked down this hallway. They walked up some sort of stairs, and they walked back down the stairs. And you can see exactly where they are in real time. Let's talk about machine learning. It's buzzword time. So I'm sure you guys have heard a lot about machine learning, at least with respect to the news coverage, if not just all over the place because everyone's super excited about it. And like the really basic idea of what machine learning is we want to learn through experience, just like you would. So if I sit in front of you and I go, what is this thing? And you're like, oh, that's a car. And after a while, you get to learn what the general idea of a car is. If I show you enough cars, you're like, oh, if I see anything with like four wheels and it has like a steering wheel and it kind of drives around, is that a car? Potentially, yeah, we think so. Um, so that's essentially the concept of machine learning. And what you're doing in the first one is classification, which is this like kind of a yes or no answer, or a set of discrete answers, which essentially means like there's a limited number. So kind of the canonical example is like, is there a cat in this picture? There's actually a lot of research using a lot of GPU time, not for gaming, but for figuring out whether or not there's a cat in this picture or not, so we can publish papers. So regression is similar to classification, but now you're trying to figure out on an infinite number of potential outputs. So like the numbers between 0 and 1, or something is kind of what the output space of that looks like. So this would be like fitting a line, like you guys have done linear regression a lot in high school, or should at some point. And that's what regression is. So clustering is, I have some sort of data, and I'm trying to figure out what the relationship between the data is. How is it related? Are there certain things about the data that are more important than others? And if they are, how does that map to my output, or whatever else I'm looking for? But if you understand nothing else, just understand the basic idea that we're learning through experience. So the first one we're going to talk about is supervised learning. So supervised learning is essentially when you know the output. So you have some sort of input X coming from your data set. It goes into your fancy algorithm. It outputs some sort of prediction, which is Y hat. You'll see these kind of, when I say hat, I just mean the little caret over the variable. You'll see this kind of formalism really commonly once you get into the field. You have some sort of prediction. You have the actual true value. So this could be like, I have an image. My image is input, and is there a cat? Yes or no. So this could be, yes, the thing thinks there's a cat, and then the actual data set says, no, there's no cat in this picture. You did it wrong. You get some sort of error, and then you try to learn from what you've made up, mistakes you've made in the past. So there's another thing called reinforcement learning, which is, you guys are familiar with AlphaStar, which is the machine learning agent that plays Dota 2. There's one that does StarCraft. I might be getting those names mixed up. And there's also one that plays Go, which is a really complicated board game. So what reinforcement learning is doing is kind of a similar thing. We're trying to learn from our experiences still, but essentially we have some sort of learner. And we have this thing called a reward function over here. The reward function is, give me a state, give me for this, like, say we're talking about chess. So based on where all the pieces are on the chessboard, I can generally, there are ways to figure out if you are doing better or worse than the other person. So if I make a move and I end up in a position that is better than you, that's good for me. If I end up in a position that's worse, that's bad. And that's all this is saying. So the learner takes in every state, every reward, and they're trying to figure out what is the correct action given any state. So any orientation of the board, any, like, you removed all my pawns, whatever it is, every possible orientation of the entire board, what is the action I should take from that state? And that's essentially just running continuously. And over time it learns, and then it can learn very complicated ideas or tasks. I show a great video. I love this video for just the simplicity of what you're doing. So this is by Google. It's the only video that's not from Georgia Tech, just because the graphics are amazing. So the idea of what we're doing here is we're playing hide and seek. So what you're going to see is some blue guys, and then some red guys, and then some boxes. You can see when the box is locked, and essentially the goal of the game is that you get reward when the red is within visual line distance of blue. So red is doing better if it's seeing the blue, as you can see right here. Blue is doing better if red is not seeing it. And blue can move these blocks and lock them so that red cannot move them. So what you're going to see right now is that they're going to block it. So they've locked the door. Now red can't get in to see them. They're going to keep getting, it's worse and worse and worse for them. So they have to figure out a way to still see blue while they're in there. And we haven't told it what to do. We don't tell it what direction to take, what possible strategy to use. all we say is this is good or this is bad. And this allows it to figure out new strategies like what you see here. So this is ramp use. They'll figure out, they're like, oh, the blue doesn't lock the ramp. I can use the ramp to jump over the wall, and then they're stuck in there and I win. So then blue's like, oh, we can figure this out. So they'll take the ramp. We put it inside our structure, we win, no matter what you do. Because you can't get past the wall and you can't get over the wall because the ramp's inside. So then we can learn more and more complicated strategies. So that was just blocking a single door. Now it's, we have to figure out a structure ourselves. That's what you're going to see here. So we're going to take these three, put them together. They're going to be locked in place. And what you can see is they've also locked the ramps so that the red can't use the ramp to jump inside the shelter. But what happens very commonly in reinforcement learning is that the agents will find a way to do something that you never thought was possible or was not intended to be possible. So blue has locked the ramp, but there's a way to exploit the physics so that the red can still move the block while it's on top of it. And what it'll do is it'll use this as to box surf into the actual shelter itself. So what they'll learn is eventually just lock everything. If they lock everything, they can't use the box to surf. And then they can construct the ramp. So this is the same thing that was used to do AlphaStar, AlphaGo, all of those really complicated things, and kind of the things that people are really interested in right now. How does it learn on its own? And the big thing about reinforcement learning is you just got to run it millions and millions of times, which is kind of what they're showing here. So there's also, that's more on those are kind of the fields that I'm more interested in. Now we're getting into stuff that I haven't had a lot of interest in, but through creating presentations like this, I find really, really cool. So essentially, how do robots and humans interact? That gets really complicated. And like I'm a more traditional roboticist in the sense that I do like control, state estimation, and I don't have this kind of skill set. And whenever I talk to these people, I always learn something like, oh yeah, that's a good point. If we're going to put a robot in the real world, we need to solve that. And it's stuff that I would never have thought of. So kind of studies of like how we can use robots to improve humans' lives. How do we interact with people? How do we know if they're paying attention to me? How do I do this sort of thing? And it's a lot of human behavior and psychology. We also conduct a lot of studies on human subjects. And this is the cool thing about Georgia Tech is that all of these different fields kind of get together, and I know students from other labs, and we can kind of collaborate on stuff. So this is not stuff that I was on. This is another piece of research. And essentially the general idea here is you have a robot, it's an emergency situation, there's a fire. Will people follow the robot? So me, in my naive roboticist fashion, I was like, yeah, people will probably follow the robot. And as long as the robot goes in the right direction, we're okay. But like if the robot goes in the wrong direction, people are not going to follow the robot. It's obvious, of course. And what they found is actually the opposite. People will kind of blindly follow the robot because it's in a position of authority, no matter what, even if it kind of leads them down the wrong path. So, and I've seen how often robots can get lost and they're not useless, can become rather useless navigation-wise. So this was really eye-opening to me. There's also more traditional mechanical electrical designs, a lot of this kind of mechanism design. What you're seeing at the bottom right is a thing called soft robotics. So this is no longer, you have that rigid thing you're working on. How do you use like membranes or just straight up pressure? And what they're using here is essentially tubes, and they're adding more and less pressure to them, and that moves the arm around. It makes the actual control of the system very complicated. But this is how we actually run and how we walk and how we do pretty much everything. So our world is kind of designed around the concept of soft robotics. Only recently have we actually been able to make any progress on using those things. So there's a lot of cool research here. We should have, so this is more on the traditional mechanism design. So a lot of times you'll see we take a robot, we put wheels on it, problem solved. On flat paved ground, we have no problem. It works perfectly every time, it's not a problem. But what if we start doing this kind of stuff? Very quickly, robots need to drive off the nice pavement and into more unknown areas. When that happens, they get stuck. And this is problematic because the hardware itself can't modify it. Like from a controller's perspective, there's nothing I can do if the robot just loses traction. So we can look at new stuff like different ways of looking, like we use walking mechanisms, or we can switch between the two. There's some research on using the auto rally platform in order to have spikes that jump out of the wheels or to get better traction when we need it. So all of this kind of wacky stuff, which is a lot of fun to do. There's also augmentation exoskeleton stuff. So this is how we want to enable humans to do more or to do what they used to be able to do. So this is a lot of prosthetics, human assist, rehabilitation, that kind of stuff, which has really interesting applications, like really interesting challenges of like, how do you work with someone? Because it's not like you have any way of effectively telling someone else how you would take a step forward, right? Like I can't tell you exactly how much each one of my tendons pressure should be applied, plus all my muscles should contract in order to do this thing. But somehow we have to do that in order to walk with you. And not only do we have to do it, we have to do it quickly, like and keep up with you walking so you don't fall over. And this gets really complicated. They're doing a lot of machine learning, kind of learning from that experience as we talked about earlier. So here we have a knee and an ankle joint, and what you'll see a lot of prosthetics has been rather stuck on, we'll just walk on flat ground. If we walk on flat ground, you don't change your gait. It's pretty straightforward. But now we're like, he's changing pace. He's walking up and down stairs. He's going to walk up and down some inclines. Like, how do we know what correct position the knee and the ankle joint should be in, let alone anything else? So that's kind of what you're seeing here. Obviously, he's strapped in because robotics. He actually has what looks like a 10 sensor on his actual thigh. So that's what can tell when his muscle contracts to give you some sort of feedback on when the leg should be moving. There's a lot of simulation in this. Really cool stuff. Okay, so that's kind of the core robotics. I think I took a little bit long. We'll kind of speed through the rest. But so let's talk about choosing a major. So a lot of times, people that I've experienced with first is that you guys have a very good experience. You come away knowing some really important topics of mechanical, electrical, software, the whole shebang. But what you do in college and what you do after you get out of first and in the actual industry of robotics is radically different than what mechanical looks like for first. There's a lot more design, fabrication beforehand, and prototyping than what you're currently doing, with a lot more math. We also have electrical stuff. So there's a lot of like PCB development and controls and signal analysis, stuff that you just haven't touched yet. And in software, like most of my day is not programming, it's reading papers and understanding the math behind what I'm doing. So that's not to scare you or anything. That just means that if this is something you're interested in, I'd recommend that you look at doing that major or look into doing something related to that, because it's very different. And it's also okay that if you don't have that background, to start in something new. Because there's no reason to be like, oh, I did mechanical in high school, like I'll keep doing mechanical forever. Like if you want to do something else, go ahead and do it. You're not like going to be super behind or anything. Most people don't have the skill set that you learn anyway coming out. Keep that in consideration. The other thing about robotics, as I've alluded to a bunch of times, it's very multidisciplinary. Like my background is in computer science, but I do the hardware maintenance for the platform that I run. I've done some light electrical prototyping for it as well, some low-level firmware. Like I'm all over the board. But I took some pictures of different stuff that my lab has been working on. The top left, you'll see a drone from Skydio. So Guy from Robojackets works at this drone company. So we do real-time control of drones. We do CPR, which you'll see in the center right here with the thing called a Lucas device or something related to a Lucas. There's the guy doing control of fusion reactors, or predicting when the fusion reactor is going to fail before it does, and properly responding and doing the shutdown procedure. There's guys in my lab working on doing stocks and how do we trade stocks and optimize our portfolio. There's also people looking at COVID and how it spreads and how we can control the spread of COVID. So the crazy thing about this is I make a car go vroom around a track, but the algorithms and the concepts that I'm designing and working with are applied to all of these systems. So not only do you have the line between mechanical, electrical, and software is not clear, and that you'll switch between them and move around constantly, and that's totally to be expected, but the actual application of what you're doing can be changed pretty drastically without changing the core of what you're actually working on. Last note I'll have is there is no way to get out of programming. It is everywhere on SAT word, ubiquitous. So all mechanical engineers, electrical engineers, compies, EE, like whatever, add in your acronym. There is programming for everyone, and that's just because it's such a powerful tool. And it might be more on the analysis side, it might be more on the CAD side or analyzing your CAD models, but at the end of the day, you're going to be programming something. It's required by all Georgia Tech freshmen to take some sort of programming course. So let's talk about skills in college. So I've talked a lot about how essentially, I don't want to say your first experience is useful, but your first experience is not directly mapped to the skills that you're currently working on, that you'll be working on when you get to college. So when you get there and you start doing this kind of research that I do or whatever, which you can totally join, you'll need to pick up a new skill set. And a lot of people are kind of afraid that like they don't know enough or they're not gonna be able to pick it up. And kind of my advice on this is, no, you'll be fine, 100%. The whole point of you going to college is to learn things, not to know things, and not necessarily to do things. So, but if you wanted to get those skills and to kind of learn more about what you need to do, this is kind of some plays I'd recommend. So the easiest one to get into is like personal projects. This is just like find something that you find interesting and then go do it. And it doesn't have to work. Like honestly, and this applies to job interviews, grad school, working in research labs, a lot of times things don't work. What I care about as an interviewing side is, did you learn something from it? And did you improve as a person because of it? And that's really the concept around these personal projects. Like, yeah, it's really cool when it works. But if you try to do this LED cube here at the bottom and it doesn't quite work out, the worst thing that happens is that you've learned things about LEDs and resistors and electronics, which is a pretty good thing because a lot of people don't know that much about that stuff, and they do things wrong. So what you're seeing here at the top is a thing called a Fruta pendulum. So that end arm is actually free spinning, and what it's doing is using the actual servo there to twist it fast enough in order to stabilize the pendulum at the top. And this is a really classical controls problem. And there's a lot of places online to look for these kind of different projects. If you can't come up with anything, you're not creative. I am not creative, so whenever I need to do something, I look up what other people have done and just kind of learn and copy from it. But maybe you guys are more creative than me. The other thing to talk about is student projects. Obviously, I'm a big fan of Robojackets. I firmly believe in the skill set that you learn there. So what you're seeing here is a bunch of the other student competition center teams from Georgia Tech. So we have a solar racing team that does a like 2,000-mile race with a solar car that they build themselves from the ground up. You see GT Off-Road, which is on the top right. They build this car from scratch. This is Motorsports. They built this car from scratch. This is, oh my God, I'm blanking on their name.
Racing.
Rec Racing. Thank you. Sorry. So this is Rec Racing, and they have a really cool challenge. They have a very limited budget, which is the amount of dollars they earn a year. So like this year, they have $2,020 in order to build a car that they then compete in a bunch of like drag races and rally car challenges and just a straight up show match of show off of the car. And you get really cool stuff that looks like this. All student built, all student run. High Tech is similar to GT Motorsports, but they do more electric focused stuff. So this is an entirely electric car that does racing. So this is more a little bit higher level than more personal projects, a little harder to get involved with. Most colleges have something related to this. Obviously, I can talk about the Georgia Tech ones because I've been involved in it, but they're really great for both leadership development and technical development. Obviously, Robojackets is the best. Not a biased opinion at all. So this is kind of some of the robots we've made in the last couple of years. So this is similar to what I do with Auto Rally. This is a battle bot. Yes, we do fight robots. It's a lot of fun. We have robots that play autonomous soccer, which is what you see here. This is an autonomous navigation challenge. This is something we built for Robot in One Weekend a couple years ago. So there's a lot of cool robots within Robojackets that work on a wide range of issues, kind of similar to how robotics is very diverse. So the other thing, I really like research. Obviously, I'm doing a PhD. And I really like to work with young undergraduates. And when I say young, I mean like freshmen, sophomores. And I'll explain this. So, and it's not just me, this is most professors. When you come in to do research or to work with me, and you're like a third year or a fourth year, most of the time it takes about a year or a semester to get up to speed on what the work we're doing is. And then, like, if you're old, you like graduate. So it's not very helpful for me. I still work with the students, but I don't have the same, like, I can't work with you over 4 years to do something really cool. But if you come in and you're a freshman, even if you don't know anything, that's great. Because then we can figure out what is important. And we can kind of focus on what you're doing into a way that'll end up somewhere that you want to be. Because a lot of people kind of don't know where they're going and kind of get lost and drift around. And then by the time they're about to graduate, they haven't quite figured out what they want to do. So if you want to do research, start early. You're not expected to know what you're doing. In fact, if you do know, it probably isn't interesting research. Like if there's an answer, they're probably not working on it. The whole point is that we don't know what the actual answer is. You can just walk up to labs and try to join them. Like email professors, try to schedule tours. It's a little weird with COVID, but everyone is working. We're continually trying to do stuff. There is never a deficiency of work that needs to be done with respect to our research lab. Most of the issue we have is that we don't have enough people, not that we don't have enough work. And even work at all levels, not just like, oh, crazy mathematical derivations. Like sometimes I just need someone to integrate a sensor into the Auto Rally platform using like straight PWM. Like not hard stuff that you can learn in a weekend, but it just needs to happen. And I don't have the time to do it. So I love working with those kind of students because then we can do something simple and then we can build on it and do something more interesting later. The other thing to point out is labs are very different. We all do radically different things, and it's all kind of weird. And like each student has their own little focus. Like I obviously do a lot of autonomous racing with cars, but the guy next to me does fusion reactors. Very different skill sets. So even just within the same lab, you can see different things. And then also across labs, you'll see very different approaches to things. So if you're looking for a lab and you're like, oh, this is not really what I want to do, try to join another one because there probably is one that is what you want to do. So I'll talk about internships really briefly. So I had 2 internships with General Electric up at their research center, which is more research focused. Think of them not as like a job, more as an extended career. And it's both for you and them. So I had one internship at a place that I won't mention, which did not go super well. The manager I worked with was not a nice guy, and we did not get along. What I learned from that internship is that I didn't want to work there, and that's fine. It's okay if that's the lesson you learn, in my opinion. So you'll kind of get a sense for what you want to do. Industry is very different than college, very different than research, and very different than student competition projects. Like everything is radically different. It's unfortunate. The skill set is not even like does not always just directly transfer. So, but again, for internships, every time when I've been ones, the ones that I thought were well done, like they kind of treated you like you're here to learn. You'll obviously do some work because you are getting paid, but it's more about you getting a feel for them and them getting a feel for you, whether or not they want to hire you full time. Robotics, like really hardcore robotics internships, are really hard to find at an early age, just because the skill set required is just something most freshmen do not have. And that's fine. Come work in my lab and we'll work on those skills. Please. It's not a problem. It's great for everyone involved. Talk a little bit about life after school. Obviously, I still haven't finished school. So I talked to some older Robojackets that actually have left tech and did not decide to stay here for a decade. So again, I have a guy that works at Skydio, which is down at the bottom. There's a guy in Robojackets, I think there's 2 or 3 at this point, that have worked on the Mars rover. There's also a lot of guys that work in industrial automation. Um, there's a lot of work in industrial automation. There are a lot kind of like robotics-y startups that you can get involved with. Artificial intelligence is probably the most widely applicable. Mechanical electrical skill sets kind of somewhat specialized. It's just kind of the way it is. I won't harp on that too much, but don't worry about industry. Industry's going in the right direction. You'll have a job. You'll be doing fun things for the most part. So I'll leave you with some closing thoughts before we get into questions. Try something new when you come to college. The big thing about majors specifically is that, like, let's say I come in, like I did computer science, but I'll talk about a guy I knew whose name is Matt. Matt came in, and Matt was not sure if Matt wanted to do mechanical engineering or computer science. And he ended up picking computer science. But then he did a lot of mechanical engineering on Robojackets. So it doesn't necessarily matter what your major is. Like when people come to work in my lab, we're doing real-time controls and all this stuff. Like I don't even ask what your major is because for the most part, I don't care. It teaches you some skill set, but most of the things that we're talking about, like it's kind of specialized and you can always pick up that skill set. So never feel like you picked a major and now you're locked into doing that one thing for the rest of your life. Ask your parents. Most of the time, they're not doing anything related to their major in college. Other thing, not knowing what you want to do is normal. The question I always get a lot is like, what kind of robotics should I do? I'm like, well, what do you want to do? And they're like, I have no idea. That's normal. I'm like that, and I'm a PhD student. So I'm a little older than you guys. And I'm still confused on what I want to do. Also, I don't know what I'm doing half the time. I'm rapidly learning new things and getting involved with new stuff and kind of picking up new skills. And sometimes I walk into the lab and they're like, all right, today we're talking about nonlinear optimization. I'm like, I don't know anything about nonlinear optimization. Guess what? I get to learn. And that's totally fine. That's what college is all about. Even PhD, and that continues forever. You can really contribute to anything. I've talked about this a couple times, how much I like working with younger undergrads. Like everyone feels like they don't have the skill set, they don't have the knowledge to do certain things, so they can never join the lab, and they should just never ask. That's wrong. We'll teach you the skill set. Usually the bigger barrier to entry is whether or not you're willing to put time in the actual skill set. Because most of the skill sets that we need help with, or like what you want to do, like sometimes they can take years to develop, but there's always something lower, like simpler that you can start off doing now that'll get you there faster. So don't worry so much about like, oh, I can't do all this crazy robotic stuff. Like, I don't know how to make a car go around a track at 40 miles an hour. Like, yeah, neither did I when I started. I like could barely program, and now I am where I am. And that's just because there's always lower level things that need to happen with respect to research and industry that you can get involved in on those simpler tasks, and then you build up in complexity over time. And that's just how it always is. So my final thought is get out of your comfort zone. This is something that I had to learn. Like I was computer science. I was like, all I do is computer science. None of that hardware stuff. It's not how robotics works, unfortunately. So push yourself to do something that you haven't done before, especially in college. You'll be very rewarded for this. The experience will be very rewarding. Because maybe the thing outside your comfort zone is actually what you really want to do. And you just don't know yet. So go out and try a bunch of things. Go take an EE class. Go work on some robot doing mechanical design if you're a computer science major. Like, we really don't care. All we care is that you're learning and improving. It's kind of important to you. So hopefully we'll do some questions now. I think I droned on a little bit longer than I was intending to. Hopefully it was all useful. Again, if you guys have any questions, my email is there. Feel free to email me. Happy to sit down and talk with teams, people, parents, whatever it may be. Because a lot of these kind of stuff is like very specific to who you are and what you want to do. So it's totally fine if you're like, oh, this is like general advice, but nothing really specific for me. But it's Send me an email. We'll figure out the specifics of you. Um, there's no problem. I think I also have some other Robojackets in the call before we start into QA. They want to introduce themselves.
Hi, I'm Joe. I'm a fifth year electrical engineering major at Georgia Tech, and I, similar to Jason, I've been the president of Robojackets. I've been doing a lot of stuff on the, I guess, electrical side, and I've done a couple of internships, co-ops, and I'm hopefully graduating this semester. So it's my experience.
Hi, I'm Todd. I'm a second year computer science student here at Tech. And I'm actually working in the Auto Rally lab with Jason right now. And then in Robojackets, I work on BattleBots, so I do mostly mechanical stuff. So I do mechanical stuff at Robojackets, but I do CS with both the lab I'm in and in my major.
Alrighty, I guess we can move on to the Q&A now. So our first question was, does Georgia Tech have any summer camps with a focus on robotics?
Oh, not that I know of. They're I knew they did some stuff for educators, but I don't think anything targeted at students that I'm aware of, at least.
Okay. And our second question, how can you deal with the fear of I can't do this because I don't know anything about it?
That's a hard one. That's a one that I'm still dealing with constantly. Like I feel like I seem like I know lots of things. Um, I think what you do is you take it one step at a time. Like at least for me, like when I read a new paper or I look at something, it's like math I've never seen before or a concept I've never seen before. It doesn't matter how long it is that it takes me. Sometimes you just have to sit down and start from square one. And even if square one is way behind everyone else, you got to start from there and build up to where you are, where you need to be. Um, I had a lot of weird gaps in my education. Like I did computer science, which didn't cover the mathematics that I really needed to know, like differential equations. Um, so like I'm like going through freshman level differential equations textbooks now because that's just what needs to happen. Um, I don't think it ever goes away. I think you just get more used to the fact that it's not that you failed by not getting there. It's just that you don't have the background to do that thing yet. So you can go and get that background. There is never any like it's just impossible or some leap that is just impossible to make. Always try to compare yourself to the person you were yesterday, not other people.
Thanks for answering that. Our next question is how to deal with ADHD.
I don't have it, as far as I know. So that's a hard one.
So, I mean, I personally have it. So
Cool.
for me, I it's tough, right? I think when you're in engineering or computer science, it's kind of hard to focus on one specific problem at a time. Easily distracted, of course, right? So I think trying to actually kind of similar to Jason's recommendation on starting new things. Similar deal for me. Like I take a problem, try to look at it, break it down, and then I take a break, right? Just keep looking at the same homework problem or just keep looking at the same engineering problem, whatever. Uh, Often isn't gonna help, right? And this can be applied to a lot of people. So starting the problem, thinking about it, but then you can take a break, do something else, even just like switch to a different homework assignment, do different class, whatever, kind of take your mind off of it, and then maybe come back, kind of try to focus again for a little bit of time, and you can get through it. So just kind of breaking it down and trying to tackle the little things. I mean, it's kind of how my personal approach has been. But that might not work for everybody, right? There are a lot of resources out there that kind of show different strategies where you can approach it. So it's kind of up to you on how what works best for you. But that's kind of what works best for me. So.
I hope that was helpful. And our last question for now, how was life during your undergraduate years at Georgia Tech?
A very broad question. So, I mean, it was pretty good. I spent a lot of time doing Robojackets, like a lot of time doing Robojackets. Similar to how I'm sure you guys are with First. When you spend a lot of time doing First, more than some people might think that you should, I did the same thing with Robojackets. I wasn't super happy with the curriculum of Georgia Tech with computer science. And that's mostly just because it wasn't exactly what I wanted to be doing, which was robotics. There were some things that were related to robotics, there were some things that were not related to robotics. And I just kind of focused more on the Robojacket side than the actual classes side. But I feel like this is a question that everyone should answer that's on here.
Yeah, so my experience, again, similar to Jason. I stayed busy with Robojackets. I was on the Club Ultimate Frisbee team and, of course, did classes. I think it's good to try, and you'll probably hear this, and this applies to high school and college and, career, whatever, finding a balance. You'll hear it a lot. You'll never figure it out. But you'll get closer and closer. So, you can't just be working all the time, because if you do that, you'll get burnt out. So, and some people, experience that in high school and college and beyond, just doing the same thing. It can get really tiring. So, I would, try to come up with a balance and try different things. College is about, new opportunities that you may not get. So, anywhere else. So, it's kind of my experience. Busy. I stay busy, but I'm that type of person. I like to keep myself busy. So
I haven't really been here that long. This is only my third semester here, but also like going from the high school I went to Georgia Tech was a huge difference in the type of opportunities that are offered. Because, for example, my high school didn't have First, and I had no experience with robotics outside of just playing with servos and killing a bunch of equipment that, if I did now, probably not be a fun time from anyone involved. But Georgia Tech is one of those places where if there's anything that you really want to do or learn, chances are there's a good place that can help you do that properly and can give you all the resources you need to be able to learn how to do that. And you meet a ton of cool people along the way too. For example, I came to Georgia Tech and didn't know anyone. And most of my friend group now, granted, is from Robojackets, but also from the other stuff I've done at Tech. And I feel like being able to explore all those options and meet all those kinds of new people has really influenced my experience as a whole.
All right, thank you all of you for your answers. Next, we have first a thank you from Mr. Lee for your awesome presentation. And he says he graduated high school in 1976. Is it still too late for me?
Definitely not. There's plenty of resources online. It is better than ever to get involved with robotics. We had a really interesting, I was talking to another guy about this last night. The evolution of the microcontroller of 2010, 2012, that kind of era, has made it so much easier to get into the basics of what we're doing than ever before. And just kind of the ability to put like you can buy a Raspberry Pi now for $5. You can essentially run a full autonomous race car, like a 10 scale, off of. And there's competitions that do that. There's videos online, and you can produce one of them ourselves at one point. And you can do like really basic visual navigation for like $200. Like it is the best time to get involved in robotics right now.
And there's also a lot of hobbyist competitions. So we actually compete in a couple. So like most of our combat robotics and our battle bots, it's not university, you don't have to be a university student to do it. There's just people who are building them in their garage and beating us. So it's really
Yeah.
and they can take the time, after work or after, whatever they do, and work on their battle bot. So looking at hobbyist competitions is a really great opportunity as well, I think.
All right, I hope that answer was helpful. Yeah,
It's
this is
hosted
awesome.
by
Wait, sorry, what was that?
there's one that's hosted by Atlanta Robotics. There's like a Atlanta Robotics competition every year. I forget the actual name of it. I'm sure if you Google around you can find it. We have like anything from more complicated to more like beginner level stuff. So there's stuff to do even local.
Okay, yeah, great information.
Sorry.
So we have just like 3 more minutes. So if anyone has any last second questions, now is the time to ask, or forever hold your peace. But if there are no more questions, then I'd like to go ahead and thank our presenters for this amazing presentation with so much information. And thank you to all the attendees for attending. Hope this was a really helpful class. This is the last session for the symposium. Hope everyone had like an amazing symposium. We have one last question. What's the best way to find out about the different robotic clubs and teams at Georgia Tech?
There are lots of events for incoming students and returning students that will cover all of the student organizations. Most of the robotics clubs are under those student organizations. Definitely check out Robojackets. You can find a lot of information online at robojackets.org. There's also like BME Robotics. There's Women's something Robotics. I forget the actual acronym. So there's a bunch of robotics organizations at GT. And the best way to find them is just to look online or to go to those new student events.
Okay, I hope that was helpful. If there are no other questions, then I'd like to remind everyone that all of our recordings will be posted on gafirst.org very soon after the symposium. So keep that in mind if you have any meetings that you missed before. And yeah, this is basically the end. Feel free to leave, or if you have any more questions, stay and keep asking. Thank you to everyone for attending.